we will solve another problem on deflection, examination problem. The question is like this: determine the deflection under the loads. Determine the deflections under the loads for the overhanging beam. For the overhanging beam shown, take E is equal to, he has given the value of Young's modulus and moment of inertia 200 dPa, and I is equal to moment of inertia of the section of the beam 45 into 10 power 6, 45 into 10 power 6 millimeter per square. So the figure is given like this. It is an overhanging beam on one side. This is the beam. So you have a load here, 30 kN, concentrated load. Support A is here. So this is C. And you have a concentrated load here of D. That concentrated load is 60 kN. So you have loads at the C and D, 30 and 60 kN, supports at A and B, simple supports. Distances are like this. All these are 2 meters. 2 meter, 2 meter, 2 meter. So we have to find the deflection under the loads. So there are 2 loads here. That means we need to find the deflections under these 2 loads. That means the value of YC and YD. We have to find YC and using mechanics method. So the first step is to find the reactions. Because we have to make the bending moment expression, we need the reactions. Reactions here are RA and RB. 2 reactions will be there. To find the reactions, we have to use the equilibrium equations. So equilibrium equations are sigma MA is equal to 0, one equation we use. Treating clockwise moment positive, anti-clockwise moment negative. So I am here now. Take the moments of all the forces including reactions about the point A. So this 30 kN is giving anti-clockwise moment, so minus 30 into 2. So minus 30 into 2 is the moment due to this. Then moment due to 60 kN is clockwise, so plus 60 into 2. Moment due to RB is anti-clockwise, so minus RB into 4. Distance from A to B is 4, is equal to 0. So from this you can get the value of RB. So RB will be, this is 60, if you, so minus 60 plus 120 divided by 4. This is the value of RB. So that is 60 by 4, that is 15. 15 kN positive, that means anti-clockwise direction is correct. So RB is 15 kN. So therefore RA will be total load multiplied by RB. So RA is equal to total load is 30 plus 60, 90. From that I have to predict the value of RB, that is minus 15. So 90 minus 15, 75. So this is also positive, that means assumed direction is correct. So this is 75. So first step is to find the reactions like this. Now according to mechanics method, we have to consider a section at the farthest region in the beam. Since here it is a simply supported overhanging beam, I will take the distance from the left end. So distance x I am going to take from here. Distance x is measured from here. So there are 3 portions here: CA, AD and DB. So DB is the farthest portion from C, and I will have to consider a section XX in this region DB now at a distance x from the end C. That means x is equal to 0 here, whereas x is equal to 6 here. 2 plus 2 plus 2. X is equal to 2 at A, x is equal to 4 at D, x is equal to 6 at B, x is equal to 0 at C. Now let me take the section XX here. I will write the bending moment expression at XX. That is Mx. So bending moment due to upward forces positive, downward forces negative, irrespective of whether you have to take left side or right side of the section. So here I have to consider left side of the section only because all these loads and reactions should be covered. That is why distance x is measured from the left end here. So if you write the bending moment expression xx, bending moment due to this 30 kN is negative because it is downwards. So minus 30 into distance from 30 kN to section xx is x, minus 30 into x. Then you have this reaction RA upwards plus 75. It is upwards plus 75. Distance is x minus 2. Distance from A to xx is x minus 2. Then you have 60 kN downward minus 60 into x minus 2. Distance from B to xx is x minus 2. So this is the bending moment expression. So according to the Euler's-Bernoulli difflection equation, this is equal to EI into d square by dx square. So this is nothing but the mx. Therefore, what I can write is equal to the EI into d square by dx square is equal to minus 30x plus 75 into x minus 2 minus 60 into x minus 4. So this equation is called as the moment equation. So equation 1. Now next time I have to integrate this with respect to x to get the slope equation. Integrate with respect to x. Now I am using mechanics method for integration. EI into this becomes dy by dx. Integration of d square by d square is dy by dx is equal to minus 30 into integration of x is x square by 2 plus 75 into this x minus 2 is treated as x. So therefore integration of x is x square by 2. Therefore integration of x minus 2 will be x minus 2 whole square by 2 according to mechanics method. So it will be x minus 2 whole square by 2. Then minus 60 into similarly here it is x minus 4 whole square by 2 plus the constant of integration c1. So this is the slope equation. If you simplify this, minus 15x square plus 37.5 x minus 2 whole square minus 30 into x minus 4 whole square plus c1. So this I call it as equation 2, which is the slope equation. Now once again you integrate with respect to x, you will get the deflection equation. Integrate with respect to x, you get EI into integration of dy by dx is y is equal to here if you integrate minus 15 into x cube by 3, integration of x square is x cube by 3 plus 37.5 into integration of x minus 2 whole square is x minus 2 whole cube by 3 minus 30 into integration of x minus 4 whole square is x minus 4 whole cube by 3 plus c1x plus c2. That means if we simplify this is minus 5x cube plus 37.5 divided by 3. So the value is, as you can see, 12.5. So 12.5 into x minus 2 whole cube minus 10 into x minus 4 whole cube plus c1x plus c2. So this is equation 3. So we got moment equation, slope equation and deflection equation. Now we have to evaluate the constants of integration C1 and C2 using the boundary conditions. Let us write the boundary conditions here. So it is not a symmetrical beam, therefore, so no boundary conditions in this case are, we have to use the condition that at the simple supports you have the deflection 0. So that means at A, theta is y is 0 and at B also y is 0. So they are the boundary conditions. So first boundary condition at A, the value of x is equal to 2 meters because x is measured from C, x is equal to 2 but y is 0, deflection is 0. Please remember that at simple supports deflections will be 0, only slope will be present. So if you use this equation 3 we have to, because deflection is 0, we know that. So substituting this in equation 3, so your LHS becomes 0, EA into y is 0 here. So 0 is equal to minus 5 into 0 is 0 x is 2, so minus 5 into 2 cube plus 12.5 into 2 minus 2 whole cube minus 10 into 2 minus 4 whole cube plus c1 into 2 plus c2. So this is the equation. So therefore what we can get here is 0 is equal to, this is minus 40, this becomes 0, 2 minus 2 becomes 0, 2 minus 4 becomes minus 2 which is negative. In Mechanis method, if you get negative term, that is neglected, this term is also not there. So you will be having only 2c1 plus c2. So we will get an equation 2c1 plus c2 is equal to 40. So one equation we got. We cannot solve this because there are two unknowns. So this is one equation. Second equation, second boundary condition, at B also you have x is equal to 6 but y is equal to 0. Deflection is 0 at support B also because it is a simple support. So once again using that equation 3, LHS becomes 0 because y is 0. RHS will be minus 5 into 6 cube, x is 6 here, plus 12.5 into 6 minus 2 whole cube minus 10 into 6 minus 4 whole cube, then plus c1 into 6 plus c2. So you get another equation c1 and c2. So minus, this is 6 cube into 5. 6 cube is 36 into 6 into 5. 1080. So minus 1080 plus 12.5 into 4 cube. So 4 cube is 64 into 12.5. It is 800. We get 800. Then 10 into 2 cube, that is 80. So minus 80 plus 6c1 plus c2. So if you simplify this, 6c1 plus c2 will be equal to, you bring all those terms to this side, so it becomes 1080, becomes positive, minus 800 plus 80. So it becomes 360. So this is second equation. So we have got two equations now. The first equation is 2c1 plus c2 is equal to 40. 2c1 plus c2 is equal to 40. Second equation is 6c1 plus c2 is equal to 360. Now if you solve these two, you can get the values of c1 and c2. Let us solve this. So 2c1 plus c2 is equal to 40. 6c1 plus c2 is equal to 360. So if you subtract one from the other, so this c2 will get cancelled. So it becomes minus 4c1 is equal to minus 320. So c1 is equal to 80. So we get the value of c1 as 80. Therefore c2 will be, let us see, c1 is equal to 80. Substituting that here in one of the equations, 2c1 plus c2 is equal to 40. So c2 will be 40 minus 2 into c1 is 80. So it becomes minus 120. So c2 is minus 120. So you can check the answer by putting in the second equation. 6 into c1 will be 480. Okay, 480 minus c2 is 120. So okay, 480 minus 120 is 360. Okay, the answers are correct. So we got c1 value as 80 and c2 value as minus 120. Once you get these two constants of integration, substituting back in the equations of slope and deflection, that is 2 and 3, we can get the general slope and deflection equations. Now let us write the general slope and deflection equation by substituting C1 and C2 in 2 and 3. So I will write substituting for C1 and C2. Substituting for C1 and C2 in 2 and 3. In 2 and 3. So equation 2 becomes now EI into dy by dx is nothing but theta. Okay, I can write this as theta. So this is theta. Is equal to minus 15x square plus 37.5 into x minus 2 whole square minus 30 into x minus 4 whole square plus C1. C1 is 80. So this is the slope equation. So this equation is slope equation. So this is equation 2. If you substitute for C1, C2 in equation 3, you will get EI into y, deflection equation, which is minus 5x cube. Minus 5x cube plus 1.5 into x minus 2 whole cube minus 10 into x minus 4 whole cube plus 80x minus 120. C2 is minus 120. So these equations I call them as 4 and 5. So equation 4 is slope equation. Equation 5 is deflection equation in general. Just by putting the values of x in these equations, we can get the required values of slope and deflection at the points. Yes. Now, what he has asked, let us see. He has asked the slope deflection values at C and D under the rules. He has asked it. So that you can get from equation 5 now. So to find YC, that is deflection at C at this point. So what we have to do is we have to put x is equal to 0 here, because at C x is equal to 0. So put x is equal to 0 in 5, in equation 5, and after substituting for x, if the term within brackets becomes negative, that term should be neglected. So that means we have EI into, I can write it as YC. Y becomes YC is equal to minus 5 into 0. So first term becomes 0. Second term, of course, plus 12.5 into 0 minus 2 whole cube minus 10 into 0 minus 4 whole cube plus 80 into 0 is 0 minus 120. So please see here, this is negative. 0 minus 2 is minus 2 negative, neglect this term. This is also negative. 0 minus 4 is negative, minus 4, neglect this term. So you left with only minus 120. Therefore, YC is equal to minus 120 by EI. Later on, finally, we will substitute for EI, and I will just show you how to get the value of deflection in millimeters. So YC value is negative, is indicated it is downward deflection. Similarly, you can get the value of YD. So deflection under the load, second load. So YD we will calculate now. To calculate YD, we have to take x is equal to 4 meters, because the distance x from C to D is 4 meters. You can see here. Put x is equal to 4 in the same equation 5. So to find YD, deflection at D, put x is equal to 4. So in equation 5. Here once again in equation 5. So what happens here? EI into LH becomes EI into YD. Y becomes YD is equal to minus 5 into 4 cube plus 12.5 into 4 minus 2 whole cube minus 10 into 4 minus 4 is 0. 4 cube plus 80 into 4 minus 120. Now here you can see this term vanishes. So you will be getting minus 5 into 4 cube, that is minus 4 cube is 64. 64 into 5 is 320. 320 plus this is 2 cube. So 4 minus 3 is 2, 2 cube is 8. 8 into 12.5, of course it is 100. So plus 100, this is 0 plus 320 minus 120. Of course here minus 320 and this plus 320 will get cancelled. So you will be left with minus 20. So therefore YD will be minus 20 divided by EI. So here also this is also minus, that means the deflection is downwards. Now let us see how we can evaluate in millimeters. So we have got YC as minus 120 by EI and YD as minus 20 by EI. Now by substituting for EI we can get the values in millimeters. Now we should be very careful here. He has given the value of E as 200 GPa, or it can be written as 200 into 10 power 3 MPa. MPa means Newton per millimeter square. So 200 into 10 power 3 Newton per mm square. Now we should be very careful here. Let us take also one unit, that is kilonewton and meter. Because here all these loads are in kilonewtons, I want to keep the load unit as kilonewton, and of course displacement spans are in meters, therefore I stick on to kilonewton and meter. That means this should be converted to kilonewton per meter square. Now let us see how we can do it. So E is equal to 200, this is 2 into 10 power 5, I can write newtons. Newtons to kilonewton is into 10 power minus 3 or divided by 1000, divided by millimeter to meter is 10 power minus 3 square of that. So you should be very careful here. Then it becomes kilonewton here, meter square here. So this is the conversion. Now let us simplify this. So this becomes 2 into 10 square. This is 10 square divided by 10 to the power of minus 6, which is nothing but 2 into 10 to the power of 4 or 10 to the power of 8. So this goes to numerator, it becomes plus 6. So 2 plus 6 is 8. So kilonewton per meter square. That means E value we have to take 2 into 10 power 8 kilonewton per meter square. So this is the conversion. So he has given in Newton per mm square, that is converted into kilonewton per meter square. I value of course he has given in millimeter power 4, that should be converted to meter power 4. He has given 45 into 10 power 6 millimeter power 4. Let us convert to meter power 4. It is 45 into 10 power 6. 1 millimeter is 10 power minus 3 meter to the power 4. So this becomes meter power 4. So if you simplify this, it becomes 45 into, this is 6 minus 12. 6 minus 12 is minus 6 meter power 4. So this is the value of I. So I value we have to take this, E value we have to take that. Now we will take the product of those two. You will be getting E into I value in kilonewton meter square. So let me do that. Afterwards we will substitute in this expression for YC and YD to get the value in meters, then into millimeters. So now E into I need the value of E into I now. E into I is called as the flexural rigidity of the beam. E is 2 into 10 power 8. E is 2 into 10 power 8 into I is 45 into 10 power minus 6. 45 into 10 power minus 6. So please see that this is in kilonewton per meter square. This is in meter power 4. If you multiply, you will get the answer in kilonewton meter square. So the value will be 90 into 10 square. You can see 45 into 2 is 90. 10 power 8 into 10 power minus 6 or 10 square, that is you can take it as 9000 kilonewton meter square. So this is the value of EI. We have to substitute here. So therefore, substituting for EI, what we will get YC as minus 120 divided by EI is what we have got. So that is minus 120 divided by 9000 millimeter. Meter. It will be meter. So the value is 120 divided by or 1 divided by 900, which is 0.01333. 0.01333 like this meter. If you convert to millimeter, you have to multiply by 1000. So it will be like this, 13.333 millimeter. So it is negative, of course. Negative means downward deflection. That's all. Similarly, YD value we have what? Minus 20 by E. Minus 20 by E. That is minus 20 divided by 9000. It will be in meter. There is 2 by 900. You can take it as 2 divided by 900, which is 2.222 into 10 power minus 3. 2.222 into 10 power minus 3 meter. Multiply this by 1000 or 10 power 3, you will get the 2.222 mm. So this is also a negative, means this is also downward deflection. So this is how you have to do the problem. After getting that, you can always plot the deflected curve here. So YC value is that is 13.333. So downward deflection. So this is your YC value. YC value. And D value, of course, YD value is 2.222 negative. So it will be somewhere here. This is shifted here. So this is your YD value. Now if you join these things, so here deflection is 0, here deflection is 0. So joined by a smooth curve. So elastic curve we are going to get. If you join those points by a smooth curve, that is the deflected curve or elastic curve. So this axis of the beam is this beam deflects like this. So just I will show you how the deflection will be. So if you can join the points like this, of course here it will take a shape like this, and here it is like this. So this is how the deflection takes place. Here there is a effect of hogging bending moment, whereas here there is an effect of sagging bending moment. So this is the deflected curve of the elastic curve. So it gives an idea, deflection gives an idea about the bending effect of the load applied on the beam. So it should not, anyway in the design, the check is the beam should not exceed the value of maximum deflection at any case. That is called as the serviceability criteria in the design of RC structures or steel structures. So this is how we can solve the problem using mechanics method.